This paper presents a new smooth parameterization of rigid body inertia. To control highly dynamic robots, we need to identify the inertial parameters of each link. Least squares estimation of each link's inertia can be performed based on offline tests as shown here, or in real time using an adaptive approach. Rigid body inertia is classically described by the mass m, the first mass moment h, and the 6 unique elements of the symmetric rotational inertia tensor I. These 10 numbers are the classical inertial parameters of a rigid body. However, it is well known that not all sets of inertial parameters correspond to some physical body. Parameter sets that do are called fully physically consistent. The inertial parameters are physically consistent if and only if the mass is positive, the rotational inertia is positive definite, and the eigenvalues of I satisfy the triangle inequalities. Estimation that does not consider these requirements often yields non-physical results. The requirements for physical consistency can be expressed in a much simpler statement that the pseudo-inertia must be positive definite. The pseudo-inertia is a symmetric 4x4 matrix with a 1-to-1 correspondence to the original set of 10 inertial parameters. Prior work explored embedding physical consistency in a parameterization using the eigenvalues and rotation matrix. Later, the pseudo-inertia was leveraged to do estimation subject to linear matrix inequalities and unconstrained estimation on the Riemannian manifold P4. In this work, we return to the idea of embedding physical consistency in a parameterization, which enables unconstrained optimization on the vector space R10. We first reveal that the eigenvalue parameterization is singular whenever the body has 2 eigenvalues that are equal. Then we explore 2 new parameterizations without singularities, the exponential of a symmetric matrix and our log-Cholesky method. We focus on the log-Cholesky parameterization because of its computational simplicity. Beginning with 10 unconstrained base parameters, we construct an upper triangular matrix U with exponentials on the diagonal. Then J is computed by a Cholesky-inspired construction, where J0 is a reference pseudo-inertia, which can be identity or based on a prior. We then extract the classical inertial parameters from the pseudo-inertia matrix. Interpreted physically, alpha scales the density, D applies contraction or elongation in 3 directions, S applies shearing in 3 planes, and T applies translation in 3 directions. The mapping from these parameters to the classical inertial parameters is closed form with a singularity-free Jacobian. While the estimation problem becomes non-convex, all local optima remain global optima. We tested these methods on a dataset of 1,000 random rigid bodies under time-varying wrenches, with measurement noise and bias. Estimation using the classical inertial parameters yielded non-physical results 15% of the time. Of the 3 physically consistent parameterizations we tested, the log-Cholesky converged the quickest and most consistently. We also tested the log-Cholesky parameterization on the MIT cheetah leg. Using 20 random starting guesses, the estimations rapidly converged to the same RMS error, and similar monotonic decreases in error were seen in a separate testing dataset. Overall, our parameterization of inertia paves the way for using easily accessible unconstrained optimization tools to enforce the physical plausibility of learned dynamic models. Beyond estimation, potential applications include differentiable physics simulators and adaptive control schemes.